Well, this is electric circuits course of second semester offered in spring 2020 to the students of electrical engineering in the Department of Electrical Engineering at UET Lahore, and I am Dr. Khalid M. Hassan. Our today's lecture is on Thevenin and Norton equivalent circuits. The textbook reference is chapter 3, section 3.4. The basic philosophy of Thevenin and or Norton equivalent circuit is that if we have a circuit, say for example, we have a circuit with some voltage source, say 15 volt, and resistance. I'll use this circuit in the following discussion and say and this is node A, B. This is the circuit, and at the right hand of the circuit we have connected some load. This load may be a single resistor, or it may be combination of resistors, or it may be just another circuit. Now, if we are interested in the load voltage and the current which is flowing through the load, we can perform mesh analysis. Yes, we can perform the mesh analysis, and knowing the load, we can find current 1, current 2, current 3, and then we can find the load voltage and the load current. Or equally, we can perform the node analysis, identifying this as a node, and yes, another node, and another node, and at the output side another node, and the bottom, the whole over here. This is a ground node, and say this is V1, this is V2, V3, and V4. And knowing all these voltages, we can find the voltage at the output side and the current flowing through the load. But if we change the loads, we have to perform the whole analysis. Again, write node voltage equations in order to find load current and load voltage, or mesh equations in order to find load voltage and load current. So due to any change in the load, we have to redo everything again. So instead of doing this, if we can find the equivalent circuit, equivalent of this, the whole over here in green box, if we can find this circuit and we represent this circuit with only two elements, voltage and resistance, and this is A and B, and on this side we have load, say for a simple case it's a resistor only. So in this case it will be very easy for us to find load voltage and the load current, even if there is any change in the load resistance. We can find the load voltage and load current quite easily because we have just a single loop. This circuit which is equivalent to the original circuit, is known as Thevenin equivalent circuit. We can also represent the whole circuit with two elements such that one element is current and other element is the resistance. So if this circuit is equivalent to the original, then we can find the load voltage and load current quite easily, because this is extremely simple circuit. If we change this resistance, no problem, we can find voltage and current quite easily due to simplicity in the circuit, because this circuit is very simple. This circuit is very simple. We can use this circuit as equivalent of the original, or this circuit as equivalent of the original circuit. This circuit will be known as Thevenin equivalent circuit, and other will be called as Norton equivalent circuit. In Norton equivalent circuit, we have a current source and a parallel resistance. In Thevenin equivalent circuit, we have a voltage source in series with the resistance. Now, how we determine the equivalence? In order to determine the equivalence, we see that, say for example, this circuit, and I want to have its equivalent circuit. Whatever is in the equivalent circuit over here, if the voltage and current with a load are same as that over here, look at the original circuit over here. If the voltage, this voltage and this current, if the voltage and current over here, if this current and voltage and this voltage and current, they are same, these two are equivalent. So how we determine the equivalent circuit? We will see that if we use Norton equivalent circuit, so we have then a voltage source which we call V Thevenin. In Thevenin equivalent circuit, we have a voltage source VT or VTH, and the resistance is RT or RTH. So only two elements in it. Only two elements in it over here. Or we can find its Norton equivalent over here, Norton equivalent, I Norton, and a parallel resistance over here. This is R Norton. And whether we use Thevenin or Norton, if the voltage of both of these two circuits is same, and the current over here, the current is same, this current is same as that of this current, then these two over here circuits are also equivalent. So either we can use Norton equivalent, we can use Norton equivalent or Thevenin equivalent, whatever. So if we have Thevenin equivalent, we can find Norton equivalent. If we have Norton equivalent, we can find Thevenin equivalent due to source transformation. So students must be aware of it. Source transformation. In source transformation, say for example, if we have a voltage source, say 12 volts, and we have a 3 ohm resistance, we can transform this circuit into a circuit with a current source and a parallel resistance over here. Okay, at present I will not use any value over here. So this is AB and AB. These two circuits are equivalent if the V open circuit in this circuit is equal to V open circuit in the second, and I short circuit of the circuit with the voltage source is equal to I short circuit at the right hand side. Now let us see what is V open circuit. V open circuit over here, V open circuit, as there is no current flowing through it, there is no voltage drop across this resistance, and V open circuit is equal to 12. This open circuit voltage of this circuit must be equal to the open circuit voltage of this circuit with the current source. Now for this, in the equivalence, we will use the same resistance, the 3 ohm resistance in series with the voltage source, and 3 ohm resistance is now in parallel with this. Now if we use same resistors, what should be over here? What should be this current? Such that the open circuit voltage of the circuit at the right hand side is equal to the open circuit voltage at the left hand side. So what current should be flowing over? We see that if 4 ampere current, if we use a current source of 4 ampere as the output is open circuit and there is no current through this branch, whole of the current is flowing through this, means 4 ampere current is flowing through this 3 ohm resistance, and the open circuit voltage in this circuit will be 12 volt, which is same as that over here. So open circuit voltages are same. If we use 4 ohm resistance and 3 ohm resistance over here, which is in parallel. Now I short circuit. For I short circuit in the first over here, I short circuit means if we short circuit these two, so what is this current? Simple loop, and the current, which is now the short circuit current, is 12 divided by 3 is 4 ampere. Now we look at the circuit at the right hand side. If we short circuit this, if we short circuit terminals A and B, this current should also be 4 ampere. Now you know this short circuit, it is in parallel with a 3 ohm resistance. So I'll reproduce over here. If any resistance R is short circuited over here, the resistance of the short circuit link is 0 ohm. So what is the parallel combination? Parallel combination or parallel equivalent is also a short circuit. And in such a case, whole of the current will be flowing through the short circuit path and no current will be flowing through the resistance. It means that the 4 ampere current is flowing through this short circuit link and no current is flowing through this. So I short circuit is equal to 4 ampere. So as the open circuit voltage in this is 12 volt and open circuit voltage is 12 volt and short circuit current is 4 ampere, short circuit current is 4 ampere, we say that these two, due to this voltage current characteristics, we say that these two circuits are equivalent. And we have discussed this source transformation in chapter number 2 before the lockdown situation. Now there are various categories of circuits. In category 1 we have circuits with all sources of independent type. All sources are independent. It means that we are using a voltage source over here and a voltage is shown over here. Say this voltage remains fixed whatever is the current. This is the definition of a voltage source. And an independent current source over here, whatever is the voltage across this current source, this current remains fixed. So in a circuit, we may have, if in a circuit where all the sources are independent sources, this is our case 1, and I will discuss an example of such circuits. So case 2, when these sources are all, I must say all over here in the first, all independent sources, all dependent sources, all sources are dependent. A dependent voltage source and current source, we use this symbol. The symbol is same for the dependent voltage source and current source, and if we show the polarity, it is a dependent voltage source, and if we show an arrow, it is a dependent current source. So this voltage source may be, this should be as, this voltage source may be a voltage controlled voltage source, it may be a current controlled voltage source, and at the right hand side the current source, and this current source may be current controlled current source, it may be a voltage controlled current source. What does it mean? You will see in textbooks or in circuits, so there may be a proportionality constant, say K, and over here Vx. This Vx is the control variable. So it is because it is a voltage across some element in the circuit, and right now circuit is not shown. So this voltage is controlling the voltage over here. This voltage is a control signal. So it is a voltage controlled. In case of voltage controlled voltage source, we will have KVX type of thing over here. And in case of current controlled voltage source, we may have a proportionality constant and some currents, IX, IY, I1, I2, I3. So in this case, the control variable is a current signal, so it is a current controlled voltage source. Now come to the current source over here. In case of current controlled current source, it may be as K, and the control variable is the current. This variable is a control variable, and this is proportionality constant or amplifying factor. So this is a current controlled current source. We may have KVX over here. In this case, the control variable is a voltage signal. This is a proportionality constant, and this is a voltage controlled current source. We may have circuits with all sources dependent, voltage source or current source, or both voltage and current sources, and all are dependent. Case number 3 is that we have both sources. Sources are both independent and dependent. Some sources are independent sources and some sources are dependent sources. In all 3 types of the circuits, I will discuss examples to find the Thevenin equivalent and the Norton equivalent. So first of all, I will present an example with all sources are independent sources. And you will see this example in the textbook. This is 15-volt source, independent, 3K resistance, fixed value, linear resistance, and a current source of 2 milliampere, another resistance of 3K. We use the label A and B of these two nodes over here. And say we have some load over here, and initially, in order to keep our discussion simple, we will say a single resistance. Now in the analysis, we can find the voltage across this load resistance and current through this load resistance. Knowing the voltage and current, we can determine the power and energy and other related things in this load. So voltage and current, these are sufficient to determine the power and energy, etc. We can find this load voltage and the load current, voltage across the load and voltage through the load, using mesh analysis or using node analysis. So if we can use mesh analysis and node analysis in order to find VL and IL, then why we discuss Thevenin equivalent and Norton equivalent? The reason is that, sorry, I need to add a resistance over here, and this resistance is over here. This resistance is 4K. Reason is that if we change RL, then we have to perform the analysis again, mesh analysis and node analysis. Change RL again, perform the analysis again, the whole analysis. There may be number of meshes and number of nodes in it. So in order to simplify our analysis, we see if we can find the equivalent circuit to the left side of this node A and B. The equivalent of this, I will show it over here again. The equivalent. If we can find the equivalent, such that it is not coming. Such that the equivalent is represented by two circuit elements, then our analysis will be quite simple, because we have one loop over here, and due to one loop we can find the voltage and current across the load resistance. If we change it, finding the voltage and current will be a simple task. Now, how to find the equivalent? In finding equivalence, we will see the V open circuit, which appears over here, V open circuit, must be equal to the V open circuit of this. And then I short circuit of the original circuit, I short circuit of the original circuit must be equal to the I short circuit of the equivalent circuit. So I will delete these things for clarity. Later I will put it back. So V open circuit and I short circuit, if this V open circuit and I short circuit of these two, this and this circuit are same, these are equivalent. And if we have A voltage source and a series resistance, this is Thevenin equivalent circuit. And if we have a current and a resistance over here such that the condition of both V open circuit and I short circuit are met, then this will be known as Norton equivalent circuit, and this resistance will be Rn and this current In, and in Thevenin this will be RT and VT. Note that in some texts Thevenin voltage is represented as VT, in some other as VTH. Likewise, Thevenin resistance RT, and some other text you will also see TH. You should also follow the textbook for the equivalence. Now, in finding Thevenin equivalent, we will find V open circuit and we will find I short circuits. So now, first of all, we find V open circuit. In finding V open circuit, in this example over here, 15 volt, 3K, 6K, 3K, and a current source over here, this current source, this is V open circuit means over here, this is V open circuit, and this is 2 milliampere. As these two terminals A and B are open circuited, there is no current flowing through it. Therefore, the voltage drop over here is V open circuit. We can use node analysis methods, we can use loop current methods, whatever method you use. Say for example, I use node voltage, so this is the ground terminal and this is V open circuit, this is V open circuit. Because the voltage over here, because the voltage, this voltage is equal to this voltage over here, as there is no voltage drop across this resistor. So I will use this label letter symbol V open circuit directly. And now I write node equation. Voltage at this node is known due to this voltage source, and I write the equation. This is V open circuit. As you know, I'm writing node equation, and if you have listened to my previous lecture, writing a node equation for at any node, we assume all the currents are flowing, and except some current source is connected to the node. In this, and in such a case, we will follow the direction of the current shown in the current source. And in this case, the current through current source is also flowing away from this node. From this node, look at the circuit diagram from this node. So this current is VOC minus 15 volt. This is the voltage across 3K resistance over here. What is this current? This current is VOC minus 0 volt, which is the ground, and the resistance is 6K. What is this current? It is shown, it is directly shown. This is 2 milliampere. I will write it as over here and like this. And this is, if we solve this equation, only VOC is unknown. Rest of things are known in it. Therefore, we can solve it easily, and VOC in this case is equal to 6 volt. So we have found one thing, open circuit voltage, which is equal to 6 volts. And this open circuit voltage in its Thevenin equivalent, circuit, it will be known as V Thevenin. So over here, so this will be 6 volt, and in the Thevenin, as in the Thevenin circuit, we have a Thevenin resistance and Thevenin voltage. This is V Thevenin. We have found V Thevenin. And now we have to find R Thevenin. In order to find R Thevenin, we can use two methods. So now, R Thevenin. How to find R Thevenin? One method is to remove all sources. Note that we are discussing an example where all sources are independent sources. So removing all sources means if a voltage source is connected over here like this, say this is terminal X and Y. So if we eliminate this, eliminating voltage source means we will short circuit this. So over here, what is the voltage? Vxy. Vxy is a V specified over here, and Vxy is equal to 0. So V across xy is equal to 0. In removing current source, say we have X over here and Y over here, and we have a current source, say current I over here. So in order to remove current source means we make current 0. So as the current source is connected between X and Y, so we open circuit it. There is no need to show these dot signs over here. We just leave it open. We have opened it over here, and it is open. And the current flowing through in either direction is 0. There is no current flowing through it. So in short, a voltage source is short-circuited. In short, the voltage source is short-circuited and the current source is opened. I don't know why it is not coming. And if we see this circuit, I reproduce this circuit. We have a 3K resistance and 6K resistance and 3K resistance terminal A, and this is B, and I forgot in it is a 4K over here. There is a 4K resistance as well. And what I have done over here, there was a voltage source and there was a current source in the original circuit. What I have done, what I will do in order to remove this voltage source, I will short circuit this. What I will do to remove this current source, I will open circuit this. So in doing so, it will be over here, I will so I have removed the voltage source, I have removed the current source, and now R Thevenin is the resistance seen from this side through A and B. Here we see that these two resistors are in parallel, and if we see these two resistances of 6K and 3K, we have 6 multiplied by 3 and 6 plus 3, it is 2K, this is 2K, and then the resistance over here, and this resistance is 4K, and resistance, Thevenin resistance is 3K plus 2K plus 4K, and this is equal to 9K. So we have found Thevenin resistance. So in here, look at this circuit. So we have found the Thevenin resistance of 9K. I will reproduce the circuit again over here, 6 volt, and this is 9K. This was A and B terminal over here. This is Thevenin circuit. I can find its Norton equivalent here. and such that this will be 9K. What will be the current? Current will be 6 divided by 9, and this current is 2 by 3. So whether we use this circuit or we use this circuit, both are equivalent. Other method to find RT, second method to find RT is first find I short circuit. I short circuit means in the circuit when everything is intact, I short circuit means I short circuit. Look at the circuit diagram. I short circuit. We have to find this current. I short circuits. In finding I short circuits, we can use loop analysis, loop 1 and loop 2 and loop 3, or we can use node analysis. Over here we can say that this is our node, ground node, this is ground node, the bottom, and node 1, node 2, and the whole is node 2, and that's it. There are 2 nodes other than the ground node, and we can use node voltage analysis or mesh current analysis in order to find short circuit currents. In order to find this short circuit current, I wanted to give you a hint. This is current 1, this is current 2, and this current 3, and this I3 is I short circuit because the direction of the I short circuit and I3 are same. Now, if I write loop equations for loop 1, for loop 2, for loop 3, mesh 1, mesh 2, mesh 3. For mesh 1, the equation will be 9K I1 minus 6K I2 is equal to, there is a voltage rise. For mesh 2, can I write equation for mesh 2? No, I can't write equation for mesh 2. Look at the circuit diagram. I can't write because in writing equation for mesh 2, I don't know what is the voltage drop. So in the mesh 2, I don't know the voltage drop across the resistance, across the 2 milliampere source. So what is the voltage drop across this resistance? This is resistance multiplied by the resultant current flowing upward. So as I have discussed these things in the mesh analysis lecture, and we see that this current source is shared by mesh 2 and mesh 3. As the current source is shared by 2 mesh currents, so following the directions of I2 and I3, we should say I2 minus I3 is 3 milliampere. This is second equation. Now for the third equation, we have to find a loop which does not consist this 2 milliampere current source, because the problem is that we cannot find the voltage across the current source at this stage of the analysis. So we can write equation for the outer loop over here. For the outer loop, we can write equation, and for the outer loop, if we write equation, so this will be voltage drop here across this 3K resistance. This is 3K and I1 is flowing through it. If I move forward over here, what is the voltage drop across this 3K? And this is plus 3K and I3 is flowing through it. And following in the loop, what is the voltage drop across this 4K? So this is 4K, I3 is flowing through it. and now this is the voltage rise, and our loop is complete. Now, instead of choosing the outer loop, instead of choosing the outer loop, we can choose another loop. Just eliminate over here, and now let us choose this loop in yellow. So writing loop equation, it will be 6k due to the direction of the loop is 6k I2 minus I1, and plus it is the voltage drop over here in this direction. Now this is plus 3k I3, and then we over here then this, and this is plus 4k I3, and the loop is complete, is equal to 0, and we have written equation for this loop as well. Remember these two equations. So this equation is essential, then this is essential, and we can choose one out of these two equations. Either we use this or either we use this. So let us use this equation over here, and we leave this loop equation. Finding I1, I2, I3 due to these loops over here, if I represent again over here, if I represent, it is 9k I1, it is minus 6k I2, and there is no I3 term over here because loop 3 and loop 1 are not adjacent loops, and the right hand side is equal to 15. The second equation, I have considered this, the second equation is 0, and this is I2, coefficient of I2 is 1 and I3 is minus 1, and the right hand side is 2 milliampere, 2 milliampere, sorry, here I have done a mistake, it was 2 milliampere. See equation 2. Third equation, this is 3k minus 3k I1, this one 3k plus 3k I1, and there is no I2 term, and I have 7k I3, and this right hand side is equal to 15. If I solve these equations, then I1, I2, I3, these equations, if I solve it, it will be 3.444 and 2.666 and 0.666 milliampere. What is I short circuit? I short circuit is I3, and which is equal to 0.666 milliampere. It is over here, it is over here. This is I3, this is I short circuit. And now R Thevenin can be found V open circuit divided by I short circuit. What was our open circuit voltage? 6 volts. This is 6 volt, and short circuit is 0.666. So this is I will see 6 divided by 0.666. and this is 9 ohm. And this way we have found that our Thevenin equivalent circuit is a 9K, I think. It is 9 kilo ohm. It is 9 kilo ohm. It is 9 kilo ohm over here. So this is A and B. Now we can connect any load in order to find the voltage across the load and current flowing through the load. Note that the Norton equivalent can be over here. The Norton equivalent can be found directly from the Thevenin equivalent, if we know the Thevenin equivalent already. So this is the Thevenin resistance we have determined using the equivalence over here, using the equivalent resistance method over here, or we have used the Thevenin due to open circuit voltage and the short circuit current. The resistance will be same. What will be this IN? This IN, the Norton current. This current is basically the short circuit current. This is the short circuit current. So the short circuit current which we have found is 0.666 milliampere. Now you can see the in the Thevenin equivalent and in Norton equivalent. I will leave it to you. Find the V open circuit of the Thevenin and V open circuit of the Norton, and find I short circuit of the Thevenin and I short circuit of the Norton. Both over here open circuit should be same and short circuit current should be same, because these two are